Well, I should think about what I'm going to say in the recording a little bit more carefully before I actually record, because in my last video I indicated that that was going to be the last video of examples with triple integrals, but that just isn't the case. I've had time to process over some more semesters, and I want to show you another example that uses triple integration that we can actually put into all three types of triple integration that we have available to us right now. And we're only going to consider setting them up. We're not going to evaluate. So here's the setup. We have a sphere, x squared plus y squared plus z squared equals 20. So the radius would be the square root of 20. And we want a region inside the sphere, but we also want the region to be satisfying this statement: z is greater than or equal to x squared plus y squared. That would be inside, a formal name would be a paraboloid, or as I nickname it with my students, a parabola bowl. So there's a bowl, vertex at the origin in 3 dimensions, opening in the positive z direction, and we want it to be in the bowl and in the sphere at the same time. But wait, there's more. And we're going to add some other details. So this solid region, we're going to utilize a density function, x plus z plus 5, and we're going to set up triple integrals that calculate the moment about the xz plane. And it says 3 types of integration. I'll better identify those as we get to them. So please note, this is indicating that it's not all going to be possible to do it in one short video, so I'm going to break it up into 2. But we need the details algebraically no matter which type of triple integral we're going to set up. So let's go a little bit deeper. So there you have it to start with. The moment about the xz plane would be the triple integral of the region y multiplied by the density function dv, and dv can be written several different ways, and here is a version of our region generated by some free online software that I'm very thankful for. So we're looking for in the sphere, but above the bowl, so we're looking to measure that region. And as I tell my students, for the basic cases that we're studying in this course, because they could certainly get more advanced, we kind of need to know what the quote-unquote top view looks like. And that top view, there's a circle here, but that circle is smaller than the sphere. The sphere's radius is the square root of 20. But that circle has a smaller radius, and so we're going to algebraically compute what that would be. What happens when z equals x squared plus y squared intersects with the sphere x squared plus y squared plus z squared equals 20. And I can do a direct substitution. X squared plus y squared is equal to z. Z plus z squared equals 20. A little algebraic rewriting: z squared plus z minus 20 is 0. And to play nicely with everybody here, I opted to find an example where we could use zero product property, or what you might just call simple factoring, to determine what is the radius of that circle. That would be kind of our top view, where everything that we're going to measure happens from the top view inside of that circular region from z is 0 to whatever that is. So this factors z plus 5, z minus 4 is 0. So this leads us to z is either equal to -5 or z is equal to a positive 4. But z cannot be negative because we'll just look at the picture. We're looking at values where z is positive only, so we will not consider that. So there is a z value. Now, that's not the end of the story. That's just a good place to begin with to figure out what's going to happen next. If z is 4, we could go right here. Let's just slide up a little bit further. Okay. 4 equals x squared plus y squared. That is our circle, which is the top view. That's the circle that we see here. We're looking down upon this region. Now, we're also going to need the side view. And the side view allows us to sort of investigate what's happening in the z dimension. Because if we choose a rectangular version of this, x, y, and z, then we could look at it as the double integral around the circle with the third dimension, the z dimension, added on. So we need the side view, and the side view is going to look a lot like a parabola. If we were looking at from the x-axis towards the origin, it's going to look like a parabola from the side. And again, I'm choosing an example where it's rotated evenly around the z-axis, because if this didn't have symmetry all the way around, we would have more details to unfold. This example doesn't quite go to that depth. I picked it for other reasons. Alright, so first step, got the circle. I've discussed there's going to be a side view, so now let's look at it more closely. Alright. There we go, the top view and the side view now available to us. Now available to us. The top view is a circle of radius 2, x squared plus y squared equals 4. If I solve it for y equals, I'll get y equals positive and negative square root of 4 minus x squared. Those are details I'll need. I know x is from negative 2 to positive 2, and y varies from negative square root to positive square root. And for the moment, I'm just going to stop there discussing what I can learn from the top view. The side view, well, that's a typing mistake right there. That is the z-axis, and I'm going to call this the y-axis, but it doesn't matter because of symmetry. Here's the sphere, radius square root of 20. Here's the parabola, and I can literally say, hey, z goes from the parabola to the sphere if we're looking at it in a vertical z sense. So the bowl to the sphere, low to high. And I have algebra ready to go for some of that, but not all of that. For the sphere, x squared plus y squared plus z squared equals 20, I would need to solve for z. And z would be 20 minus x squared minus y squared in the root. And we would be looking at the positive part only because this visual is entirely above the xy plane. Z is positive in this region. We are not looking at negative z values. So, the moment the y multiplied by the density function, here's our density function, considering the boundaries, the circle helps give us the xy plane, and I just mentioned what the z boundaries might look like. To put it all together into a rectangular form, it would look like this. Remember, you do have a pause button. X goes from -2 to 2. Y goes from negative square root of 4 minus x squared to positive square root of 4 minus x squared. And z goes from the parabolable. Remember, these are z equals boundaries here because that says dz. And that's y equals boundaries and x equals boundaries. From the parabolable to the sphere, and y multiplied by the density function dz, dy, dx. Could we rearrange the order of these? We sure can, but not in this video. Now, I also want to do cylindrical coordinates. Cylindrical coordinates are, well, they can be described several ways, but I have a nickname for them. Polar plus z. Polar plus z. And from up top, we could learn that theta is 0 to 2 pi because this region rotates entirely around the z-axis, and that r is from 0 to 2 all the way around this circle. And those would be my boundaries in the polar sense. So now let's slide the paper up here. 0 to 2 pi, 0 to 2. Okay, so let's work with that. So theta 0 to 2 pi, r 0 to 2, and z, oh, I didn't talk about that anymore. Well, I cannot leave x and y in an integral that does not allow for x and y. So x squared plus y squared is r squared. And 20 minus x squared minus y squared is the same as 20 minus r squared. R sine theta is y. R cosine theta is x. Z, well, z is z. And then remember this r? When we convert to polar or cylindrical form, dy dx has another factor of r multiplied by it. Now, there is the moment around the xz plane set up in two of the three forms that we have. So, which version is missing? Well, that's right, spherical coordinates. I don't think spherical coordinates are the easiest way to evaluate this particular integral, but I like to have a little fun sometimes. And so in the follow-up video, the next one, I am going to show you how to set up the same moment in spherical coordinates. And eventually I'll get the links to both videos into each other's description, so you can always click back and check one if you happen to miss it. Until next time.